We had a nice lunch and a nice break, and thank you so much for coming back on time, and it's great to be on time for this next session, which I think is going to be particularly interesting on peatlands and forestry for water. Can I just remind you again, and I'm sorry to keep saying this, just reach into your phones and make sure they're on silent, or just turn them off if needed. And the hashtag is Source2Tap 2022. So peppered throughout what we heard this morning was mention of peatland and forestry, and I think now it's time to get into the sort of nitty-gritty of it, and I'm delighted to introduce Phil Jordan, Professor of Catchment Science at Ulster University. And Phil is going to give presentations on peatlands and forestry, and then he will be joined by William McIntosh, Asset Data Analyst in Northern Ireland Water, and we'll be able to have the chance to have a bit of a Q&A for everyone at home watching virtually. Please get your questions in on Slido, and similarly here, put your hand up, get in a Slido, whatever you want, and we'll try and have some engagement then with both Phil and William. So please welcome Phil. Before he talks though, I gather we have a short video, so enjoy this.
So the Interreg 5A funded Source2Tap project has been restoring an area of peatland which was previously planted with conifers and trialling different restoration methods to find out which is the most effective. Approximately 68% of the island of Ireland's drinking water comes from peatland, whilst up to 75% of its soil carbon is in the form of peat. In catchments such as the Erne, however, when the peatland dries out, it can release carbon dioxide into the atmosphere and earthy coloured carbon compounds into the water, and these compounds can really cause challenges for water treatment. Restoration work aims to re-wet the peatland and reverse these processes, thereby improving water quality and enhancing an important globally rare habitat. 32.9 hectare test site here in Tullycherry Forest is next to the internationally designated conservation site of Pedigo Plateau, and this was planted by Forest Service NI in the 1960s. The peat was prepared for planting using double moldboard ploughing. This leaves a characteristic ridge and furrow pattern which needs to be levelled out to ensure that the water table is able to recover sufficiently. If you have a high water table, the critical sphagnum mosses can recolonise. Their spongy structure can retain moisture and prevent the bog from drying out, and it's partially decomposed sphagnum that eventually makes up a large proportion of the peat material.
The pilot aimed to look at how well a restoration technique called cell bonding was able to help the water table recover when compared with the traditional method of drain blocking using peat dams. The aerial view shows how the site was split into 3 sections for different methods of restoration. This centre section of 8.2 hectares was the flattest, and so was chosen as the intensive restoration area to trial the cell bonding technique. This area to the southwest was of similar size and topography, so was used as a control area aimed to replicate what the Forest Service would do when leaving a site unplanted for restoration. Minimal restoration was carried out in this control area. Across the remaining area, which covered around 12 hectares, all forested drains were blocked every 12 metres or 30 centimetre fall in ground level. Accurate height information is required to ensure an even recovery of the water table, so surveys were undertaken using drone and handheld GPS units.
Cell bonding is a construction of watertight cells made from low peat walls. These walls are around 40 to 50 centimetres high and are constructed at a 90-degree angle to the slope, with bunds approximately 20 metres apart or less on steeper ground. Finger bunds are then constructed at 20 to 40 metre intervals in line with the slope. These join the parallel bunds to prevent lateral erosion and wave action. Firstly, a short section of trench is dug through the oxidised top layer of peat and any stumps which were in the way removed. This step's important as oxidised peat and rotting roots form pathways for water to escape. The digger then constructs the bunds from saturated peat dug from a borrow pit within the cell. The saturated peat is watertight and prevents movement of water. The borrow pits are then filled with brash and stumps to prevent deep holes which could be dangerous to wildlife. Diggers use existing brash mats to travel across the site and construct the bunds.
The The contractor used peat dams to block drains and brash mats, as well as building a cell-bund wall for 500 metres along the southern boundary of this control area. These measures were intended to mimic what Forest Service would do to allow an area to restore. The remaining area of harvested land was restored using a popular method of peatland restoration, using peat dams. This involves blocking each drain at 12-metre intervals, or placing one drain for every 30-centimetre drop in ground level. Dams were constructed using a digger, which dug a 50-centimetre notch into the sides and base of the drain. Saturated peat from below and bog surface was then compressed into the drain to form a peat dam. The water table was monitored using piezometers, and results were compared between the different treatments.
By restoring and protecting peatland using techniques trialled at Tullycherry, it's clear that nature-based solutions can play a critical role in delivering key societal outcomes, key economic outcomes and key environmental outcomes. The ecosystem services that the site provides, it's a globally rare habitat, and it gives us improved drinking water quality through raw water, improved biodiversity, and it really helps us to tackle climate change in the long term. Restored peatland also enables bogland to act as a filter for water, naturally improving the quality of any water leaving the site and entering the treatment works. Tullycherry is part of a long-term strategy. Over the next 10 years, the Source to Tap pilot site and other sites that we're working on will continue to recover. They'll be thriving with insects and bird life, and they will store carbon, which will help us to combat climate change for centuries to come.
So hello, I'm pleased to present some results from this part of the project. And as you probably see from that presentation, the real work has been done by others. I just get to present it here to you. And William McIntosh from NI Water and Kevin Aitchison from Ulster University were centrally involved in these two parts of the project, initiating the trials and monitoring. And our role as a university, we're a teaching and research institution, so it was always important for the separation between any trial, any works on the ground, to separate that from the research and monitoring, just to provide a bit of a reality check and to give these trials a fair test. So in terms of the peatlands, client has disconnected, it says. Sorry, one sec. Yeah, so just to add a bit more information to that. So what we decided to do with these parts of the project, and in fact the colour turbidity and MCPA dynamics in our land incentive scheme, was for Ulster University to provide a doctoral scholarship for this work, and to include all the field work as part of the doctoral training. So back to the peatland. The issue really, and that's been pointed out in the presentation, the video, that this water colour that we see in our freshwaters is caused by dissolved organic matter, which of course is prevalent in peatlands. And colour has to be removed once that water gets to the treatment plant, so that's an expensive process to clarify the water. And it's caused by fluctuating water tables. So in extensively drained peatlands, water tables tend to fluctuate between rainfall events, and that oxidizes the peat, the organic matter, and we get a colour production. And in fact, it's not just a fluvial process or a fluvial issue, we get production of carbon dioxide as well. So there's a sweet spot in terms of water table level Low variations, we reduce that colour, but we also reduce the gases that we're concerned about in terms of greenhouse gas emissions. So in this particular part of the project, the solution was to restore peatlands following deforestation. And it took place on the Tullechurry area of the Pettigo Plateau in County Fermanagh, not too far away. Next slide, please. So the map at the bottom left here shows approximately where that site is. And you can find this area on Google Maps. It's very interesting to see if you can get historical views of Google Maps. And we've, in fact, got an aerial photograph going back to 1958 to show this back before forestation. But this is the deforested area around that site. A small lake to the north here, and the border is just off slide. 30 hectares of lodgepole pine, Clearfail in 1920, and 3 restoration treatments for this part of the project were proposed with 1 untreated area. And the idea was, as part of the monitoring, to look at shallow groundwater, water table fluctuations in that shallow groundwater, but also the colour production following deforestation. Next slide, please. That's it. So there are the 3 treatments. Next slide, please. In the centre is the cell bunding, which we spent a lot of time undertaking because it's a novel treatment. But we also looked at something called wave drain blocking, and I'll explain a little bit more about that in a second, and boundary drain blocking. And in the bottom there, you can see that open moorland section. We treated that as an area that we'd like to restore back to in terms of water level conditions, groundwater fluctuations and colour. So that's our open moorland. Next slide. So, wave drain blocking and boundary drain blocking, there were new terms to me beforehand, and I guess what I've tried to do is put this together in a short cartoon here, where we've got an open drain in a deforested area that would have been put there as part of the afforestation, where water escapes from that site, and you can see with it being a cut drain into peatland, it induces that fluctuating water table. So in terms of a boundary drain block, what we do is use the peat itself to block the end of the drain around the boundary of the treatment, and hope that that's going to attenuate the water and reduce groundwater level fluctuations and hence colour. Next slide. And wave drain blocking in the top left treatment is where you take that boundary drain and you just work it upstream or up drain every so often, and hope that you'll get extra effect from that kind of extra blocking within each drain. And that's done extensively over every open drain that was leaving that particular treatment. Next slide. And the novel technique is the cell bunding, which is quite destructive because we're not dealing with open drains that have been put there for a long time. It's re-engineering the landscape surface and trying to hold back as much water as possible. And in this novel technique, cell bunding, there was 145 cell bunds completed over about 6 hectares. Central site is about 8 hectares overall, but cell bunding covered about 6 hectares. Now, there were 2 novel treatments used in Northern Ireland at the same time in different projects. There was a cell bunding in this project, and in another project, because the site lent itself to it, on the Antrim Hills, as part of Caffrey's work, they used stump flipping and smoothing. So that's exactly what it says on the tin. A stump is pulled out, turned over, and the ground smoothed, and monitoring taking place afterwards. Now, the idea was, in this particular project, to monitor colour as it left the site in surface runoff. But this site didn't have any discernible open water streams, perennial streams leaving the site. Hence, we looked at shallow groundwater fluctuations and colour production at the place where it's actually produced. And this is the kind of instrumentation we had in place. Now, you're going to have to scroll through this in a second. There's a little animation there in the top right. We have these dip wells put in place where we measure water level once a month. We suck out the water and measure that for colour parameters. And we also complemented that by hourly measurements of water level, just to make sure that our monthly measurements weren't being compromised just with that coarser time scale. So there's a little animation at the top here just to illustrate what we're talking about, this colour fluctuation. It goes up after a rainfall event, it goes down again. Press, that's it, after another rainfall event, it goes up and down and up again, and eventually we get that colour production through that oxidation of the peatland. And that's the thing we're trying to solve in this with these treatments. What's the best treatment? Now, clearly what we're doing is monitoring something directly after very invasive treatments and trying to see how this really works immediately post-restoration. Now, in any kind of literature or report that you'll see, peatland takes a long time to recover. And we were really encouraged by another peatland restoration following deforestation in the Glenderg forest, so we took our lead from that. And over about a decade to 15 years, we saw a really good establishment of peat moss. So we weren't expecting too much in this project, but what we were trying to hypothesize was that we would be moving towards the open moorland conditions after several years. So next slide. And these are the main results. So this is our test, and there's a lot going on in this graph, so I'll take you through it. On the x-axis at the bottom, we've got the median water table depth below the ground surface. So the ground surface is here, and so that's 10 centimetres below the surface, 20 centimetres, and so on. And here we're looking at fluctuations in water table over the period of our monitoring, which was 12 months. And on the y-axis, we've got our colour parameter, which is just absorbance at 254 nanometers. And again, we've got zero colour, as in, the colour of water as it comes out of your tap, and quite coloured water as we go up the y-axis. And so here are the median values in each one of these coloured dots here, and the error bars are just the maximum and minimum ranges we found in each. Now, look, the open moorland one gives us the least water table fluctuation and the least amount of colour. So that's where we're aiming to get to. And I guess what we're seeing from these results is that the treatments going right up to the cell bunding show more fluctuation and more colour in the time that we're measuring. So what does this actually tell us? It tells us that where we're trying to get to, next slide, and the next slide, is a hypothesis. We have all the conditions in place now to monitor that over the next several years, whichever resource we can find to do that, to follow its progress from being a highly disturbed engineered site to how that recovers towards open moorland. So the first year of monitoring is just showing us the effects of that heavy machinery on site and nothing else, as far as I can tell from a scientific point of view. And then over the next several years, we've got the opportunity to monitor these different treatments to see how they recover towards the open moorland. And it's not just water, what we'd like to put in place, because research provides answers as well as more questions, is to see how these different treatments recover in terms of their gaseous emissions. Okay, so carbon dioxide and methane are the big gases that are produced from these peatlands, and we need to see how they recover. And if these treatments stay static, and if this one, as we suspect, is more dynamic and moves towards this ideal condition. So further monitoring is required at this site, is the key take-home message from this restoration. Okay. So I think that's it for these slides, and we're going to move on now to the next short video on the forestry part of the project.
The Source to Tap Interreg 5A funded project is piloting various methods to reduce sediment in drains and streams following harvesting at forestry sites. Water from peaty catchments can contain significant quantities of suspended organic material, which gives it a dark colour. as well as creating challenges during drinking water treatment, evidence suggests excessive sediment can negatively impact fish spawning success. The measures aim to either reduce the amount of sediment entering waterways or encourage suspended sediment to settle by slowing or diverting the river's flow. All methods piloted were in addition to existing protection measures implemented on site. The measures were implemented at 11 Quilcha and Northern Ireland Forest Service sites in the Erne and Derg river catchments. Time-integrated sediment samplers were used for monitoring. These have an inlet and outlet, and as water enters the pipe, it slows down, allowing sediment to settle out. The average suspended sediment load over a period of time can then be calculated. The devices were placed in small, unclassified streams or forest watercourses, into which the harvested area drained. The Source to Tap project planted a cover crop at a site in Glenderg Forest. The crop consisted of 30% Yorkshire Fog, 30% Highland Bent and 40% hard fescue. It was sown by hand on a 200-metre stretch of stream bank over a width of 10 metres. Within 1 month, the roots of the grass began to bind the soil, and after a year, the cover crop was well established. Sediment levels were monitored up and downstream of the cover crop and at a similar sized area of unsown ground. The cover crop stretch saw a 28% reduction in sediment entering the stream compared to the unsown area. However, a cover crop planted at another site in Loch Ulton, County Donegal, didn't show a reduction in sediment between the sown and unsown areas. This may be related to site-specific factors such as soil type and gradient, which need to be investigated further. Another type of measure made use of check dams to slow the flow of the waterway and encourage sediment to settle. Dams of various materials were trialled, but all were low cost and readily available, ensuring harvesters could replicate any successful measures. The materials used were geotextile, peat, large longitudinal logs, sawn timber and brash bundles. The check dams were placed in small unclassified streams and forestry watercourses that drained tree harvesting areas, and sediment was monitored upstream and downstream of the dams using the time-integrated sediment samplers. The best performance was observed with geotextile dams. 4 were placed in a series at a site 250 metres downstream from a Forest Service NI compartment. The stream drains into the Mournbeg River, part of the Foyle Special Area of Conservation designated for Atlantic salmon. Sediment load was reduced by 68% downstream of the dams compared to upstream. At another site in Grouse Hole, County Donegal, 2 geotextile dams placed in series reduced sediment load by 25%. Longitudinal log dams also performed relatively well and were trialled at 2 sites. At Grouse Hole, the log dams resulted in a 27% reduction in sediment, and at Glenderg Forest there was a reduction in sediment of 34%. Dams of other materials saw inconclusive or less impressive results. A series of peat dams were placed in a small stream in Glenderg Forest, but were found to be unsuitable following one high-intensity rainfall event which damaged the dams and significantly reduced their effectiveness. Future interventions using peat dams in similar upland catchments are not recommended. Check dams constructed of brash and of timber were also trialled, but external factors meant the results were not viable. The final intervention made use of an existing gravel pit at a site in Grouse Hole. The aim here was to divert the flow of water into an area where sediment could settle. The pit previously received overflow from the stream during high flows and only required minor earthworks to enhance the settlement area. the altered pit recorded the best results of all the measures trialled and reduced sediment load by 69%. It also provided a new habitat for wildlife, including frogs. Piloting different measures of sediment reduction from forestry sites has provided useful information about their effectiveness. With climate change likely to bring about higher intensity rainfall events, the importance of finding catchment-based solutions of reducing sediment loss from the land is clear. Further details of the pilots can be found on the sourcetotap.eu website.
Okay, so for the forestry part of the project, again, the pilots were run by William McIntosh and the monitoring by Kevin Atchison at Ulster University. So we just go into the next slide. Yeah, that's it. So just to summarise again what was in the videos, the issue is about suspended sediment and turbidity that has to be removed once it gets down to a treatment plant. So that cloudiness or opaqueness of water, we call it the turbidity. And it's caused from erosion of land, and in this case, when we get a clearfilled area, you can imagine that that's very destructive and there's loose soil, and that during rainfall events, not all the time, but only during those short events, that suspended matter can get into the water and cause high turbidity. So it's increases in suspended sediment in natural runoff during rainfall events. And the solution that we put forward was to increase the sediment attenuation of these natural or made small watercourses or drains, leaving deforested areas. And we did that in a number of ways. In stream, so if you think about putting something in stream, we call that a leaky dam. It's not a dam that holds back the water completely. Water's allowed to go through it, because we're not attempting to turn off the tap completely at this end of the scale, but just to slow it down and to reduce the amount of suspended matter in the water. So that's a leaky dam. And then offline, so not in the stream itself, so we just divert off the water, if it's possible, into a small settlement pond. And that can be, it's not going to be possible at every site, but we can make use of that where we've got that feature. And thirdly, cover crops. So this is not actually trying to slow down the sediment once it's in the watercourse, it's trying to slow it from being mobilized from that disturbed soil surface. And we did this in the two catchments, parts of the two catchments, in the Derg catchment in County Tyrone on sites run by the Forest Service, and also sites in the Erne catchment in County Donegal by Quilcher. Next slide, please. Now, this map was on the video, but it's worth dwelling on this for a moment because it shows what the challenges were in trying to do this kind of work. This is not science that can be done in petri dishes or test tubes, things that we can highly control and keep the same. Not even on horticultural or agricultural plots on research farms. These are working forest coops. So forests that were there, they're deforested and then replanted. And we had to go in there knowing that when this deforestation was going to take place, well before it took place. So a lot of meetings, a lot of time with Quilcher and Forest Service, trying to find coops that we could actually get to within the time frame of the project. And not only that it offered the kind of environment and circumstances that we could do our monitoring. So a lot of, it's almost like a super eclipse of things coming together that we could actually go out and do that work. And the yellow sites are in the Glenderg Forest, a number of different measures chosen, so we're not doing kind of multiple treatments as we did in the other site, or multiple wells or whatever it might be. There could be lots of different treatments, in both sites and the green areas down here in the Erne catchment. So, you know, not ideal, but that's the reality of us working in a working forest rather than a controlled forest environment. Next slide, please. So just to clarify a couple of things on this best practice plus method. So we've got a typical deforested coop here. This is just before deforestation. This is just an example, with those forest drains leaving the site. And what Quilcher or Forest Service have to do as part of the quality control is slow down the amount of sediment leaving that deforested site. So they might put some measures within or just downstream of their forested coop. And we call that best practice, and we saw evidence of that on the ground. And then we've got a reach of the stream further downstream where we put a series of extra measures. So we increased them or augmented them through this in-stream, offline, or cover crop. Cover crop will be up here in the coop measures. And then we put our second monitoring device down below here. So anything that was reduced in terms of the two measurements, we called sediment attenuation, and a positive percentage there was a success. Now, the other factors that were measured in the video were things that we couldn't control, like extra sediment coming in from the side here. And we might measure that as more sediment being collected in the downstream monitoring site, and that gives us a negative attenuation. So that's something that's out of our control, and not necessarily because the extra measures haven't succeeded. So we monitored suspended sediment against best practice plus, and we reported the difference as a percentage change in sediment attenuation. Next slide. And this is, you know, a thumbnail of this monitoring setup where we had these time-integrated sediment samplers, and this is taken straight from the literature. These are well-established methods now, and the idea is that they will capture sediment as it's flowing in high flow. So we install them at low flow conditions just above the water level. So when the water level rises in the drains, they capture that flow and they capture the sediment. And that's a standard method if you want to do these things over lots of sites without employing very intensive and expensive capital equipment. So that goes into the stream and it's emptied once per month, and the sediments go back to the lab. The sediments are settled out and dried in an oven and weighed afterwards. And we collect these data over 12 months. Next slide. Now, just cutting to the percentages without actually going into detail about the maths behind the attenuations, these are the sites here, the different sites, C for Quilcher, FS for Forest Service, and the different kinds of measures we put in place here. And the settlement pond, the offline settlement pond, was only capturing water at high flow. The pond was isolated at low flow, so it's only in action at high flow. And we found that it gave a really great sediment attenuation. So worth exploiting if those kinds of features exist downstream of deforested coops. Not always there, but really worthwhile exploring. And then a series of geotextile dams, longitudinal dams, where we put the trunks longitudinally in the stream network or ditch network, geotextile dams and so on. And then we get down to the negative figures down here, where again, what we're saying is that these are factors out of our control, not because the dams didn't work. We know that they do work because we've got positive results up above. It's where we get sediment coming in from the sides that affect our experiment. And the peat dam, we had to completely disregard those results because it just didn't work. Okay, so I've highlighted cover crop as one treatment here where we got a positive result and a negative result. And looking at the slide of the second site, I could actually see just by looking at hydrology that we were probably bypassing our cover crop there. So that's something to consider. But next slide. The key findings are that, you know, it's not rocket science this. If we increase our measures downstream of best practice, we're likely to increase our sediment attenuation. So that's a strong recommendation to Forest Service and Quilcher. In fact, 2 or 3 extra features downstream of those features that are already in place to make up Best Practice Plus will take the tops off those suspended sediment and hence turbidity concentrations during storm events. And the next slide. And lastly, cover cropping. We were taken with this just because of the speed of the establishment of this particular section of cover cropping with natural grasses. That is after a couple of years, natural regeneration. This is after 1 month. So we think there's probably, again, as I said, research gives you more questions as well as answers, and we think that wider cover cropping could be something to research in future, just to solidify that surface following that quite destructive deforestation process on these peat soils. So I think I'll leave it there. Is that the last slide? Yes. Thank you.
Thank you, Phil. William, I might ask you to come up. So we have about 10 or 15 minutes to talk. I mean, it's just so interesting. If there's any questions from the audience, just put your hands up, and we've got some questions already coming in. I mean, I suppose, first of all, Phil, how much, just in general, do these kind of projects allow you to experiment? I mean, between the cell bunding and the sort of the different options with the forestry that you just outlaid there, I mean, it does seem like you are experimenting with new techniques as well.
Yeah, and I think, some of the things that Mark Horton mentioned about what held us up in the project didn't help in that regard. We had the lockdown to deal with, which reduced our time resource. And what we'd like to have done, scientifically, in a place like Tullichurry would be to have 3 or 4 cell bunding treatments to monitor, and 3 or 4 open moorlands, and 3 or 4 wave damming sites, and that gives us some statistical rigour. We get around that a little bit by putting the statistics on having multiple wells inside each treatment. So there is ways around that, but we have to work with different agencies. We have to build their timetables into our timetables, and we do the best we can.
The cell bunding is interesting. I mean, am I right in saying that was inspired from projects in Cumbria? Is that correct?
Yeah, so cell bunding was usually used on sort of sites that were cut over and on flat sites. So we had a look at it, and we were sort of approaching it from a water quality point of view, attenuating all that water and slowing it down was going to help, reduce the colour runoff.
And I'm just thinking about, for example, cell bunding on areas I've been to, for example, that would be sloped. Would it be suitable for that or not?
No, it mostly has to be used on a flatter slope. And that was some of the challenges of the project, was to try and get it to work on our site, which was a bit more, had humps and hollows. So
yes, yeah.
Getting the levels right there was important as well.
And I suppose, Phil, getting nature to do the work. I mean, part of me, when you were just talking about the clearing of the water from forestry, you sort of think, bring back beavers, or bring beavers here. The idea that nature has the answers, the solutions are there, and that nature can do an awful lot of the work for you once you put those sort of nature-based solutions in place.
Yeah, I think not just in the examples that we've seen here, I think nature-based solutions are getting a lot of attention now, and it does the work for us, which reduces the costs, but it might be that nature knows how to do this best anyway, so I think it's worth pursuing. And
we heard earlier, Phil, about the interactions with farmers and advisors, and a lot of the efforts going into getting the trust of farmers and working with them. In this case, you're dealing with agencies. Can you talk a bit about that? I mean, obviously you're a scientist, but getting agencies on board to experiment in this way, is it a long process? Are agencies much more open now, given the challenges?
Yeah, I think there are challenges there, but I think we had a very good relationship with these agencies from the start, and there were lots of meetings and site visits, and I think that was rightly so, because these are working forests. They have their own schedules and timescales. you know, these sites can be, I suppose, scheduled for felling years in advance. Indeed. And so we come along as a project and try to fit in with that timescale. And it may be that we've had to disregard certain sites because the felling was the year before or the year afterwards. It's a short window. But on the whole, the relationships with the agencies were excellent. And
the opportunity to scale up the project, I mean, is it there if the funding was there?
I think these are, especially with the forestry, the messages are solid. You know, we are recommending that they increase the number of measures they put in place themselves downstream, and to look at other opportunities, not just the kind of measures that they might be used to, but also the research questions are clear as well. We'd like to look more closely at cover cropping.
It was interesting, William, that some of the most effective measures were the low-cost materials. I saw this with the Permussel project in the west of Ireland, where it was just very similar, the leaky dams, trying to pull back the sediment going into the rivers. I mean, what can policymakers learn from that? That sometimes the things that really work are the low-cost versions, the kind of things that are around you, like the logs you were saying there as well.
Yeah, the whole point of the project was to supply sort of a low-cost, easy accessible dams. Really, the concept's quite simple, just to slow the water. So it was kind of down to getting a bit creative and look around and see what was there. My favourite was the brash dams or the twig dams. I just walked about the forest floor and picked up a few twigs and bound them together and then put them into the stream. So yeah, and I feel like they could have worked better had they been in another situation where, you know, sediment hadn't been washed in from other areas. So. And the peat dams, I mean, presumably that was a bit of a disappointment, but a very clear result, which is that they just don't work. Yeah, I think with the peat dams, we'd been out to the site in dry weather and kind of just misjudged the size of the stream. So, and we heard earlier on that it was one of the wettest years on record in the catchment. So some of those storms just completely washed them away. And we had to look again at that. So. Phil, I wonder, given we're in a climate crisis and it's, you know, we have the unpredictability associated with that, how difficult does that make your job with this kind of research? I'm not sure whether it's difficult, it just makes it very interesting because we know there's lots of questions to answer and lots of opportunities for research. So, yeah, I mean, taking Tullichurry, for example, this was a water quality project when we're looking to see whether that bog restoration had the objective of reducing colour. But clearly, carbon emissions are also really important. Colour is part of that carbon cycle. But, you know, water table level in peatlands has to hit a sweet spot, so we're not increasing the CO2, but also reducing or maintaining the methane. So there's a lot of research to do there in our environment, I think. I want to fly through 2 or 3 questions and then we're going to break for coffee. Some excellent results, but only good if they are implemented by the forestry industry. Are there indications that they will carry out these methods? Well, William wrote a really extensive review on measures for both forestry and peatland, and the results have been written into reports as well, which are available on the Sources Tech website. And it's fair to say that for the forestry report, the results section and the literature review, both Forest Service and Quilcher had a really strong input. So they're clearly interested, and you know the results they're not complicated to implement, and you'd hope that they would be taken up. Yeah. William, could adding these mitigation measures after extensive Clearfail operations have a positive impact, i.e., where it wasn't done initially? Yes. Anything. So we worked on the best practice plus measures. So best practice now is to put maybe one of these textile dams in. So adding more definitely reduces the sediment further. Yes. So, yeah, that's what the project's found. And finally, Phil, were benefits in terms of reducing flow rates observed useful for natural flood management? Yeah, that's something that we may have put in place, but because we're dealing with a temporary installation of monitoring methods, we couldn't put in place the kind of flow monitoring that we would have liked to have done to measure flow attenuation, but clearly those could be considered again in a different project.
It is just so interesting. Thank you both so much for that. We're going to break for a quick coffee and back in 10 minutes, but first just thank Phil and William. Thank you very much. Thank you.